So yesterday we talked about how our unifying principle for this particular portion of our studies is that physical forces affect the movement of all matter on Earth and throughout the universe. Our big idea is forces change the motion of objects in predictable waves. And yesterday we looked at how one, forces change motion. Two, force and mass determine acceleration. And three, forces act in pairs. Today we're going to talk about something we're going to talk about how force transfers momentum. And yesterday's discussion question on the Newton's cradle, which was pretty cool. They had some really good combinations that they were using with that, relies on using momentum to transfer energy. Those balls in the center didn't move because the energy was transferred through them to the balls on the other side. They were the recipient. Those balls on the other side received that energy. So what we want to talk about is the fact that objects in motion have momentum. And momentum can be thought of as inertia for moving objects. It's the tendency of a moving object to keep moving at a constant velocity, and it depends upon mass and velocity of the object. And the formula for momentum is mass times velocity. The symbol, believe it or not, for momentum is a lowercase p. So it would be abbreviated as P equals m times v. So momentum, like velocity, is a vector. If it has size and direction, it has two variables. Therefore, we have a vector instead of a scalar quantity. So in this case, momentum it is similar to velocity in that regard. We also have the adding of momentum. The adding of momentum to two objects is similar to adding net force. A force on an object changes the object's momentum. The change in momentum is equal to the force on the object multiplied by time over which the force is acting. So the other thing is momentum can be transferred from one object to another. Momentum is transferred during a collision, so there has to be direct contact or direct impact for momentum to occur. Colliding objects exert equal and opposite forces. Newton's third law, for every action there's equal and opposite reaction. So these forces are working on each other when they're in contact. The forces in the collision change the velocity of each object involved. So it changes speed and direction. And of course we have, as some of you very correctly pointed out in your responses, we get potential and kinetic energy happening at this as well as the transfer of force through momentum. The other thing is that we also have conservation of momentum. Again, we're back to this conserving of something. So in any case where there's no outside forces acting on a system, the total momentum of the system will not change, even if the momentum of the individual parts changes. This conservation of momentum is most easily seen in collisions where the forces are acting against each other at the same time. Now, these forces can be unequal, and the very best way to describe this is a bug hitting a windscreen or windshield when you're driving forward, okay? So obviously the momentum of the car is transferred to the bug, and the momentum of the bug is transferred to the car. We don't feel that force that's been enacted by the bug because of its small size, okay? And most likely also because of its speed. It normally is a poor outcome for the bug, right? So change in momentum for two colliding objects is also equal and opposite. The total change in momentum is zero. That's a very brief crash course on momentum. I also have attached for you for today a momentum video from Bill Nye. It's a 20-minute video, but it does a really good job of explaining what momentum is. All right? Have a good day. Don't forget you've got your quiz today. And I'd love it if we had all of our work done by the end of today and we were all caught up in science. Thanks. Bye.